AI coding tools write highly plausible syntax. They correctly format loops, invoke standard libraries, and return values that look correct on a quick read. But that plausibility is a danger. They guess at logic, and a confident guess often masks a fatal flaw. In the previous episode, we explored Agent 12, which handles conceptual reasoning. But reasoning about a problem is entirely different from deploying code to a production server, where strict mathematical demands apply. Looking at this grid of 30 agent architectures, we enter the software development tier. We start with Agent 13, the code generation agent. This tier represents a strict departure from probabilistic chatbots. Here, the focus shifts entirely to verifiable engineering. True software autonomy requires eliminating the guessing entirely. The system must transition from merely suggesting a block of code to mathematically proving that the code works under stress. The baseline workflow for a standard IDE copilot is linear. A human writes a prompt, the large language model outputs a block of code, and the interaction ends. This creates a dangerous trap. An LLM might generate an e-commerce checkout function that processes valid payments perfectly, but completely lacks the validation logic to reject a negative charge. It looks correct, but it operates as a liability. Because these systems lack an internal verification loop, human engineers are forced to catch these edge cases. Highly paid developers are reduced to acting as a manual QA department for a machine, bottlenecking the entire development cycle. When that human review inevitably fatigues, a silent logic bug slips past the bottleneck and executes in production, causing active data loss. A common industry reaction is attempting to engineer better prompts or relying on newer models with larger context windows to prevent these logic errors, but the prompt is not the issue. The missing component is an autonomous verification architecture that forces the LLM to validate its own work against objective criteria. Any agent operating in a production codebase must follow a single rule: never trust a stranger's code, and that includes its own. The solution is test-driven generation, or TDG. This adapts the methodology of traditional test-driven development specifically for autonomous systems. TDG enforces an absolute constraint. The agent must write and execute a machine-readable test suite before it is allowed to write a single line of implementation code. This aligns the software engineering process with the scientific method. The generated code acts as a hypothesis, the test runner serves as the experiment, and the stack trace provides the raw data. The first step is the red phase. The agent runs its newly generated tests against an empty codebase. They must fail, and fail loudly. This proves the tests are active and correctly targeting missing functionality. If a test passes before any code is written, it is a fake test. Deliberately failing first proves the system is setting a trap with actual teeth. Standard code completion tools output code and immediately forget the interaction. Test-driven generation creates a stateful, multi-turn loop where the agent remembers its previous attempts. Verification acts as the steering wheel. The LLM is forced to continuously rewrite and adjust its logic until the execution data perfectly aligns with the test contract. This diagram illustrates the multi-agent orchestration architecture required to power the test-driven generation loop. At stage 1, the orchestrator node receives a feature request, decomposes it into language-specific tasks, and manages the dependencies between them. Control passes to stage 2, the tester node. Operating in the red phase, this specialized agent analyzes the task and writes a failing test suite focused explicitly on edge cases. Stage 3 is the sandbox. The tests run in an isolated Docker environment using real execution frameworks like PyTest or Jest, ensuring the code interacts with an actual file system. In stage 4, the developer agent enters the green phase. Its sole objective is to write the absolute minimum amount of code required to satisfy the assertions in the test suite. If the assertions fail, the refinement path triggers. Factual stack traces from the test runner are routed directly back to the developer agent, forcing another iteration. Once the tests pass, stage 5 introduces the refactor node. The agent cleans up duplication and technical debt, immediately rerunning the tests to guarantee the cleanup introduced 0 regressions. Finally, at stage 6, the code is proven. Execution logs are saved to the persistent memory, and the orchestrator advances the system to the next task. Because this architecture runs on LangGraph, it maintains a persistent state graph. The agent retains the full history of every failure and the precise stack traces that caused them, preventing it from repeating mistakes. This cyclical trap ensures that the agent cannot proceed until every assertion passes. It is the only reliable method to verify a baseline of zero regression code commits before a human ever reviews the pull request. To see how this executes in practice, we look at the book's case study, Building a Python backend function designed to calculate shipping costs with tiered discounts. The tester agent evaluates the requirements and autonomously generates several test cases, including a critical assertion called test negative weight, which expects the system to throw an error if a package weighs less than 0. The developer agent then writes the initial implementation. It correctly handles the base rates and discounts, but it fails to include the validation logic to reject negative weights. Inside the sandbox stage, the PyTest runner executes the code against the tests. The test negative weight assertion fails, throwing a raw value error because the function returned a negative dollar amount instead of stopping the process. The system intercepts this failure, parsing the raw Python stack trace into a structured JSON payload for the language model. Confronted with this objective feedback, the developer agent rewrites the function to include the missing exception handling for negative numbers. By accumulating these specific failure trace contexts, the system narrows the LLM's operational boundaries. It cannot hallucinate the same missing logic twice because its prompt now contains the exact error caused by its previous attempt. The sandbox runs the updated code. The exceptions fire correctly, the assertions hold, and the entire test suite flips to green. The agent validates its logic by providing raw evidence that the code satisfies each test. This specific mechanism bridges the gap between probabilistic guessing and deterministic engineering. Agent 13 excels in specific, definable operational boundaries. It is ideal for generating complex backend APIs, building comprehensive test suites from scratch, and modernizing undocumented legacy code. Pointing the tester agent at a brittle legacy codebase forces it to write explicit tests for every existing behavior. This creates an immediate safety net, allowing the developer agent to refactor the old code safely because any deviation triggers a failure. However, this architecture fails entirely on subjective tasks. If you ask the agent to make a user interface look more premium or adjust a layout to feel more modern, the system will break down. Every requirement carries a complexity budget. If a human engineer cannot write a definitive pass or fail assertion for a task, the agent's loop will spin infinitely, constantly attempting to satisfy an unmeasurable goal. These deterministic loops are migrating out of abstract frameworks and directly into developer environments. They execute natively through command line tools and background container processes that monitor code state in real time. Agent 13 is a highly specialized scalpel designed for definitive logic problems. It is not a paintbrush for exploratory or aesthetic coding. Achieving a green-tested pull request provides empirical evidence that the implementation handles every assertion in the agent's test suite. But in enterprise software, functional compliance is only the first hurdle. Perfectly functional code can still quietly leak personally identifiable information, send data to non-compliant regional servers, or rely on outdated cryptographic protocols. That gap requires a completely different layer of oversight. The code generation agent hands its verified output directly to Agent 14, the security-hardened agent, which analyzes the implementation solely for regulatory and operational permissibility. True software autonomy requires stacking verification, compliance, and continuous self-improvement into a unified pipeline. You can review the complete LangGraph architecture, state dictionaries, and execution code for this process in Chapter 9 of Imran Ahmad's book.